Hi, my name is Brian Caffo, and this is the lecture on multivariable regression examples. This is part of the Coursera Data Science specialization, co-taught by my co-instructors Jeff Leek and Roger Peng. We're all in the Department of Biostatistics at the Johns Hopkins Bloomberg School of Public Health. Okay, so let's start with the Swiss fertility data again, or not again, but let's start with this. And to get this data set, you just do library data sets, and then data Swiss, require the package stats and require the package graphics to get this nice pairwise scatter plot here. And this is from I believe this is from the help file for the Swiss data set. Anyway, this is a nice way, it's probably better to blow it up, but this is a nice way to investigate the relationship between all the variables in this data set. Let me go one step further and show you the help file. So if you do in our question mark then Swiss, if you do that command right there at after you've correctly loaded the datasets package, then it tells you about this dataset, and it's the standardized fertility measure and then a bunch of related socioeconomic indicators for 47 French-speaking provinces of Switzerland in about 1888. It's kind of a famous data set. So our outcome that we're interested in is fertility, all 6 variables are expressed in terms of percentages from 0 to 100. And so one of the predictors we want to use to predict fertility is the percentage of males involved in agriculture as an occupation. We want to include the ones who receive the highest mark on any Army examination, and so on. There's the education beyond primary school, the percent Catholic as opposed to Protestant, and then infant mortality. And then it says all but fertility give proportions. So anyway, you can do help data. It helps Swiss to learn more about that data set, though it mostly just contains that file, but it also gives you some references, I believe. Let's just do the first thing that we might think to do is we want to use these variables to predict fertility. So why don't we consider a linear model with no interactions? And if you do a tilde and then a period, then that just includes all the variables in the data frame as predictors. And this data equals Swiss just says look in the data frame Swiss for everything. And then when you run it, summary just runs the output. It's usually, by the way, preferable to assign your output to a variable and then do summary of that variable, but so it all fits on one line. I do it this way. And here's our coefficient, and here's the table, here's our coefficients, and we get, I want to point you to this number, negative 0.1721 right there for agriculture. Let's focus on that number. So agriculture, remember, is expressed as a percentage, and the estimate is negative 0.1721. So we estimated an expected 0.17 decrease in standardized fertility for every 1% increase in the percentage of males involved in agriculture, holding the remaining variables constant. That would be the interpretation of our negative 0.17 coefficient. And if you look back, our t-test for that is significant. What I found interesting about this data set when I was kind of playing around with it, I just looked in R for some examples of multivariable regression data sets, and this one came up. But then, I ran the marginal estimate, the one that disregards all the other coefficients. So in this case, instead of doing fertility equals dot or tilde dot, which fits all of them in the regression model, I did fertility tilde agriculture, which only includes agriculture, and you see the estimate there is 0.19, but notice it actually reverses sign, and it's also significant. So that's kind of interesting. So let's talk about that. So one thing that's worth talking about is how can an adjusted estimate, how can an adjustment reverse the sign of an effect? And I go through a simulation here just to prove it to you that it can happen. You can look at the simulation settings up here, and what you see is that the relationship between x1 and y is 95, and then after I include x2, it's -1. And I did it so that all the p-values are ridiculously significant, 10 to the minus 68 and 10 to the minus 79. So what does this look like? What does this look like? Well, what happens here is here's y and x1, and this is the unadjusted one, and you see this nice relationship. But you also see that this other variable, x2, is really quite correlated with x1, right? So it's the color is x2. So when this, and the colors change along this gradient. So the relationship between x1 and y seems to be pretty related to this relationship between x2 and y. And what regression sort of does is it looks in a level of x2, and imagine within a level of x2, if you looked at them all, if the relationship was sort of linear in this kind of smaller dimension, it's sort of hard to visualize. So what we could do, remember, we've talked about this, is to try and remove the effect of x2 by taking it out of x1 by fitting a linear model of x1 is the outcome and x2 is the predictor, and taking the residual, so that's that guy, and then taking y where I fit y is the outcome and x2 is the residual, and that's that guy on this next plot. And you see that once you factor out x2, then you have a relationship in the opposite direction. And it's basically just saying if you were to kind of fix these colors, the colors are all binned, but if you were to sort of fix these colors, then what you would see is within a color a negative slope between y and x2 and x1. Okay, so it is possible, of course, when you adjust for another variable for this for a coefficient of interest to reverse its sign. So in this data set, the sign reverses itself with the inclusion of examination and education, both of which are negatively correlated with agriculture. Right, so the higher the percent scores for the higher the percentages for examination and education, the lower the percentage of males working in agriculture for those provinces. Remember, again, this is 1888. The correlation, in fact, is this negative correlation is negative 0.64. And education, by the way, I'm saying education and examination, but they're, these are kind of measuring the same thing. They have a correlation at 0.7. So the obvious question is, which is the right model? The marginal model that disregards education, or in this case, if you kind of put in these other things, it doesn't reverse sign, or the model with education and examination in there, which then causes this agricultural coefficient to reverse the sign. So which one, with those guys in or with those guys out, is the right model? Okay. So one could conjecture in this case is whether or not this positive marginal effect is an artifact for not, say, having accounted for education level. Now, how to interpret this is a little bit difficult, and it depends quite a bit on the setting. At the bare minimum, what one could say, and in this data set it seems reasonable, is that if someone were to fit this marginal model and were to claim that, let's see, where's the marginal model? Darn it. Oh, there it is. if someone were to claim that this marginal effect of 0.19 is conclusive proof that an increasing percentage of males working in agriculture reduces fertility rate, I don't know, for whatever the reason, there would be some skepticism. There would be some skepticism that you could, and criticism that you could levy at that model by saying, well, if you were to include education, not only does the effect not hold up, it actually reverses itself. Now, selecting the correct model is actually a quite difficult subject. There's several things that you would want to balance. One is, something that reverses the sign, but is kind of obviously meaningless from the context, is maybe not something you would want to include either. So the way to go about these things is a balance between the meaningfulness of the coefficient, a collection of model building exercises where you add and subtract covariates, and thinking along the lines of the interpretation. The way I actually like to do it more than anything else is I like, when fitting regression models, to kind of craft a story. And in this case, if my story was, I think that agriculture causes increased agricultural employment causes decreases fertility rates, what I would say is, okay, given my full data set, what would my critics obviously say of me? And in this case, my critics would have a lot of ammunition, and that would allow me to revisit my hypothesis. So that's usually the way I like to think about these exercises, but there's an entire branch of statistics called causal inference, and in that branch they talk about how one can really try to navigate these thorny issues of taking observational data and trying to make more causal or mechanistic claims. Otherwise, you're kind of back to this sort of heuristic approach that I'm sort of advocating for, unless you're willing to take more classes and learn a lot more about this stuff. So let me just, I want to show another little fact so you know why these things pop up. What if I include not just unnecessary variable, but kind of clearly unnecessary variable? So the information from the variable agriculture is already, of course, contained in the model. Consider the model where we put in everything. But imagine if I created a new variable that is just this sum of agriculture and education. And clearly Z can't add any new information in this model. If we know the agriculture status of the province and we know the educational status of the province, then we know Z. Conversely, if we include Z and remove agriculture, then Z does contain relevant new information, because we need both agriculture. We need any two, whether it's Z, agriculture, and education. We need any two of those. We know the third, but including any two, if we were to include the third, it has to contain extraneous information, because we perfectly know it if we know the other two. So what does R do when we put in something completely meaningless in this linear sense? And that's this discussion only holds for things where it's linear, right? If I include agriculture squared, of course I know agriculture squared if I know agriculture, but that's not a linear function of the variable. Anyway, if you include a linear function of variables that are already in the model, then when R fits the model, it says, oh, wait a minute, you've already included variables that, if I know them, I linearly know Z, so this contains no extra new information, so I throw it out and I put an NA there. And so that's why you see these NAs pop up in R, is because that variable is linearly related to the other variables that are included in the model. Okay, so let's switch gears a little bit and talk about dummy variables, and I have this slide called Dummy Variables Are Smart. So they're not dummies at all. So one thing that you can do with multivariable regression, or linear regression, but this is interesting in the context of multivariable regression, is to fit factor models that include like a mean for group 1 and a mean for group 2 and test the difference in the means. That doesn't inherently seem like a regression problem, but in fact it is. So imagine if our variable x is, instead of the only two values it takes, is 1 if it's in a group and 0 if otherwise. So treated versus not in a clinical trial is a great example. Okay, well then for the people in the group, right, the linear model predicts this: expected value of y is beta naught plus beta 1. And for the people not in the group, then xi would in that case xi would be 1. And then for people not in the group, xi would be 0, and then this term would drop out, and then the model would predict that. So this is basically saying there's a mean for people in group 1 and there's a mean for people in group 2. And we can actually interpret what beta 1 means in this case, the coefficient in front of x1. Let me get rid of some of those marker drawings so I can draw some more. So notice what beta 1 is if we subtract these two, it's the difference in the means between. So this was the group, the mean for all the observations in group 1, and this is the x equal 1 group, and this is the mean for all the observations in the x equals 0 groups. And so if we subtract those two, we get beta 1. So beta 1 now is interpreted as the increase or decrease in the mean, comparing those in the group to those not. Okay. In this case, right, if beta 1 is positive, then that is the increase for the group where x is labeled 1 relative to the group is x is labeled 0. If beta 1 is negative, then that is a decrease in the mean for the group where x is labeled 1 relative to the group where x is labeled 0. Note, by the way, again, just by the rule that we had on the previous slide, if you know if you know someone is in group 1, let me say this. So if xi1 is our variable that's 1 for those in the group and minus 1 0 for those not in the group, then including a variable that's 1 for those that are not in the group and 0 for those who are in the group, that variable just turns out to be 1 minus xi1. You can double check that, but it's pretty clear, right? When xi1 is 1, it's 0. When it's 0, it's 1. So it just reverses the 1s and 0s in this binary variable. So this is a linear, and and our intercept is a regressor with just a 1. So this guy is exactly a linear combination of our existing variables, right? So it can't provide any new information, so it will give you an NA. Okay, just like on the previous page. So that's this point right here, which says including a binary variable that's 1 for those not in the group is redundant, just like we talked about in the previous page. And there's nothing specific about two groups, treated versus control. We could do factor variables with multiple groups. Let's say it's a 3-factor level. So imagine you wanted a predictor to be party affiliation: Republican, Democrat, Independent. Those are the most prevalent, the 3 most prevalent U.S. political affiliations. So imagine a model now where yi is beta naught plus 1. That's an indicator if you're a Republican, and 0 if you're not a Republican. So if you're a Democrat or an Independent, and we're assuming everyone in this data set falls under one of these 3 categories. xi2 is 1 for Democrats and 0 otherwise. Okay. Then let's look at what happens. Then the expected response for Republicans is beta naught plus beta 1, because beta naught is always there. xi1 is 1 when the person is a Republican, so we get a beta 1. This guy's 0, okay, and this guy's expectation is 0. So we get that for Republicans. Similarly, we get that for Democrats. And then for Independents, both this guy and that guy are 0, so we get beta naught. So how do we interpret these coefficients that come out of the linear regression model? Well, beta 1 is then, if we were to subtract these two, the beta naught would drop out and we would get beta 1. So it's clear that beta 1 compares Republicans to independents. Beta 2 compares Democrats to independents because it's just subtracting these two. So that, notice what that means is none of our coefficients compares Republicans to Democrats. What compares Republicans to Democrats is a function of our coefficients beta 1 minus beta 2. And notice this is all predicated on which one we chose as our reference category, right? We elected in my previous slide to have xi equal 1, say, be treated in 0 equal control. And then we would get one interpretation. If we did xi equals control and xi equal 1 as control and x equals 0 as treated, we would get the opposite interpretation. In this case, we have to choose. We included a binary variable for Republicans, a binary variable for Democrats, and omitted the binary variable for independents. If we had omitted the binary variable for Republicans and included the binary variable for independents, then in that specific case, the Republicans would be the reference category. They would be the ones with only the intercept. So choice of the reference category changes the interpretation. Then the beta 1 and beta 2 from the model would be corresponding to comparisons relative to the Republican reference category. Now, because we omitted the independent xi, then everything is interpreted relative to the independence reference category. Okay? Let's go through an example. Here's a nice categorical example where they sprayed a bunch of insects and they got the count of I think, can't remember if they're counting dead insects or live insects. Let's well, it depends on your opinion. If it's a nasty insect like fleas or cockroaches, let's assume they're counting dead insects. If it's a nice insect like ladybugs or butterflies, then let's say they're counting live insects. Okay, so let's assume that's the case, and then we want to let's just spray, of course. So they're of course counting they're probably kind of nasty insects, so cockroaches or fleas or something like that we don't like. Then they want to see which one of these insect sprays, if the mean count for each of the, I don't know why that's doing that, differs for each of the groups. Now there's clearly some problems here. These are counts, so we shouldn't be fitting them in a linear model, but we're going to do it anyway. And there's clearly a variance issue, right? These guys, first of all, there's an obvious effect. You don't really need a lot of statistics to see that C, D, and E seem to have a lower effect or have a different mean than A, B, E, and F. And you don't, you can see this variance problem, that the variance is not constant within groups. So the constant variance is clearly a problem. And then the fact that it counts, clearly that's a problem also. So all of those are issues. All those are issues in this data set, but we're just really trying to use it to illustrate group factors. So let's actually do it. And this will show you how the model can quantify the changes in those means. Again, pointing out all these caveats on why this isn't a terribly good analysis. So summary just gives the summary of the output. LM is our linear model function. Count is our outcome in this case. Number of insects we zapped with this particular spray. Here's the spray. Is the factor variable that has all the levels. Okay, so when you put a factor variable in, R automatically creates the dummy variables for you, and it uses the one that's the lowest order factor, and if it doesn't know, it uses the one that has the sort of alphanumeric lowest value. In this case, A has the lowest value, so it's the reference variable, but it picks that for you, and we'll show you in a slide how you can reorder it. So data equal inspect sprays tells you which data you're looking at, and then just coef from the summary function is just grabbing the table. I just wanted the table. I didn't want all the other output because then it gets too big on my slide. Okay, so what's important to note is that right here, right, it has every spray B, C, D, E, F except A, and that's because R has elected to choose A as the reference category. So this coefficient for spray B is the estimated expected increase in insect count comparing spray B to spray A. And it's B minus A, okay? And this is for expected count for spray C minus spray A, okay? And you can double check, right? Like, so spray A has a lower coefficient, spray A has a lower coefficient than spray B. Spray B has a higher coefficient. Spray C has a lower coefficient than spray A. Spray D has a lower coefficient than spray A. Spray E has a lower coefficient, and spray F has a higher coefficient. So let's double check, just make sure it makes those make sense. But C, D, and E have these really small p-values and gigantic t statistics. So let's just double check and make sure that's what's going on. Yep, C, D, and E were all lower than spray A, and it's clearly that should be significant. So that's the table's kind of working out the way we'd hope, or the way it must. Okay, let me just show you that you get the same thing if you code it exactly yourself. So imagine this indicator is just, this double equal sign is just testing the Boolean value of whether this spray happens to take the value B, and then I multiply it by 1 because it changes it from Boolean to numeric. And then the I is just a function in R you have to do if you're doing some mathematical manipulations in a model statement, which is what follows a tilde sign. Okay, so I put, this variable here, which is included in the regression model, is 1 if spray is B and 0 otherwise. Okay, and so this just hard codes all the 0, 1 variables. You could actually just put them in the data frame, you could do them, but I'm doing them in the model statement here. And you can see you get the same numbers, right, as before, right? So 0.833, negative 12, negative 9, negative 11, there they are again. You can see they're the same. Okay. What happens if we include all 6? Okay, what does it do? Well, first, so I'm including an extra variable, and this one is clearly redundant because let's say, so I have x1, x2, x3 up to x6 that are all binary, right? And x6 is equal to 1 minus x1 minus x2 minus x3 and so on, minus x4 minus x5, right? So we have, by including the intercept, we have a 1 in the model, we have x1, x2, x3, x4, and x5 in the model. So if we know all those, then we know x6. And that's, of course, just saying that if we know you're not spray B, C, D, E, F, then you must be spray A. That's all it's saying. But it's also relative to our rules that's saying we know that the indicator of whether you're spray A happens to be a linear combination of the other sprays and variables that we've included in the model. So this variable must be redundant, so when R fits it, it's got to give it an A. Now R has to have a rule for picking which one of these guys is redundant, and it's doing the last one, and because it doesn't know anything about the letters in the way that I've formulated the model here, right? It just has a bunch of 0, 1 variables. But when you include spray as a factor variable, it does this for you, and it doesn't even put the NA in the output. So that's nice. So you never kind of do things this way. I was just showing it. Well, I sometimes do them this way. If you want to be 100% sure that you have your dummy variables set right, then you do them yourselves. Otherwise, you can just trust the factor, that treat a variable as a factor variable, and it'll usually do it correctly. Here's another interesting fact, right? So on the previous page, we talked about how x6 is a function of the others if you include an intercept. You need that 1. If you don't include the intercept, it's not a function of the others, right? It's no longer redundant. And then what happens, right, is then here, if you omit the intercept, then it includes all 6 sprays. Um, and so that, that again makes sense, because now spray A isn't a linear combination of the other sprays. The spray A indicator is not a linear combination of the other sprays. But it's basically just saying, think about it this way. There's 6 means in this data set. And then the intercept gives you the mean for spray A in this case, and the intercept plus beta 1 gives you the intercept for spray B in the case where we include the intercept. So there's 6 means, so we can't kind of include a 7th, in there, and so there's 6 means. So there's really that's all we can fit. So it can only really fit 6 coefficients. So if we include the intercept and there's 5 sprays, it's got to get rid of 1 and have only 5 coefficients, because 1's going to the intercept. If we omit the intercept, then we have 6 means that we need to fit, and we have then 6 coefficients that we can fit. And it says, oh, okay, well, I'll do that. I'll include 1 for spray A. And what you'll notice then, in this case, now the model is yi equals, let's say, xa plus, I need an eraser. Is that y is equal, I'm just going to kind of do pseudo notation, is equal to beta A xa plus beta B xb plus beta C xc, and so on, right? And so the expected value of yi, if that happens to be in spray A, it turns out to be beta A. The expected value of y, if it happens to be for spray B, it turns out to be beta B, and so on. That's the model in this case that we fit. And so these should be these should be the means for each group. Okay, and so let's double check that. So spray A, it's saying the mean should be about 14, and for spray B, the mean should be about 15. For spray C, it should be about 2. Let's just go double check back here, and it makes sense, right? Spray A mean about 15, spray B, somewhere around 16, spray C somewhere around 2. Okay, that seems about right. These are the medians, but it's close enough that we know. And what I'll tell you, you can check this yourself, and it's maybe a little bit hard to see why it works out exactly this way, but these are exactly the mean. So if you just calculate the mean of the counts in group A, it'll be 14.5. If you calculate the empirical mean of the counts in spray B, it'll be 14.5. So if you do the outcome, you do your factor variable, and you omit the intercept, then it will fit a term for each one of those, and the interpretation of the terms will be the mean for that group. And if you want to compare A to B, then you have to subtract 14 and 15. Now, you don't have the right standard error, so you don't have a p-value or a t-statistic, but that would give you the correct estimate. And what you'll notice is, if I were to subtract 14 and 14.5 and 15.3, then I get exactly 0.833. I get this value right here. In other words, the models are perfectly consistent. If you're going to fit 6 means any way you do this, and the models will always be consistent. So if you parameterize the model so all the coefficients are interpreted as A as the reference categories and change from A, then they will be consistent with this model where the coefficients are interpreted as the means for each group. And if you were to subtract any of the two groups, you will get, or if you were to subtract any of the groups from A, you will get the coefficients that you had from the model where A is the reference category. If you were to subtract the coefficients from B, you would get the coefficients from the model where B is the reference category. Oh, here I actually do, where I just take the average of the within each of the groups, and you can see it's 14, 15, 2, 4, 9. That's exactly what we got right here. Okay, so at any rate, my points. Let me see. My points. Okay, If we treat spray as a factor, R includes an intercept and omits the first level of the factor. And then all of the t-tests and all of the coefficients are interpreted except the intercept are comparisons of that spray versus spray A, and the intercept is interpreted as the mean for spray A. Okay, that's the right there. And the other group means are the intercept plus their coefficient. Okay, if we omit an intercept, then it includes all terms for all levels of factors, and then the group means are the coefficients. And the t-tests are no longer for comparisons between the groups. They're tests for whether or not the groups are different from 0. And then if you want a comparison between, say, B and C or model C, what you could do is you could refit the model with C as the reference category or B as the reference category. Okay, that's the kind of lazy way to do it. I'll show you well, I don't know. That's the intellectually lazy way to do it. The lazy but knowing how to do it way to do it is to simply use the relevel function. This is just basically saying I want C to be my reference category, and then I just fit my ordinary thing, and then now spray C is my reference category. Notice there's an effect for A, B, D, E, and F, and an intercept, and C is the one that's omitted. Now this 12 is the subtraction between spray A and spray C. Okay? And so your p-value is interpreted as a comparison relative to spray C. And then just because I'm this kind of person and I like to futz around with things at this level, you could actually figure out how to do it manually. So, if you were to, for example, fit the model where A is the reference, what you could do is you want to subtract the B and C coefficients and get the comparison between B and C. Well, the variance of that is the variance for the B hat for spray B plus the variance of the B hat for spray C plus minus twice the covariance. Okay, so here we've fit the linear model where A is the reference category, and then here is just subtracting the B and C coefficients, which will correctly give you the thing as if you would fit C as the reference category, but it doesn't give you the standard error. Okay? And then let me just take the summary of that fitted model and just assign it to a variable. And then what I want to get is the standard error of that comparison, and that's the let's see, so that is the this guy here, right? That's this term. This is this term, and then minus twice the covariance is that term. Okay? And there's our t-statistic being the sum, the effect divided by the standard error, and the p being the absolute value of the t-statistic, the p-value being I always take the net. So right here's our t-statistic. We want the probability, if it's positive, of being above it. If it's negative, we want the probability of being below it. And so I always just take the absolute value, get rid of the sign, and take the negative one, and take the probability of being below, because that forces it to be below 0. I should have put, let's see, I should have put a 2 there, or twice that, if you want the two-sided p-value. The other thing I would say is, by the way, this covariance unscaled gives you the covariance not scaled, and so you have to multiply it by the residual standard deviation. Okay, and my out is, I'm defining just the set of things that I want to output, call it that, I'm giving it a bunch of names, and there you go. Round out 3 just means print it to 3 digits. So there's my estimate, there's its standard error, and there's its t-statistic. And so let's compare that in the previous page to the one where C is the reference level. So B minus C here is 13.25, and here it is spray B minus spray C when C is the reference category is 13.25. The standard error is 1.61, 8.25, and then 8. You can see they're the same. So that's how you can do it without from the model that you actually fit, right? So you know what parameters you want, and you can calculate the variance, and you can just do it. Of course, that's not how you want to do it, right? You just want to re-level it so that C is your reference level. It's so much faster. But anyway, I don't know. This trick comes in handy for me sometimes. Okay, so some other thoughts on this data. Just I want to indemnify myself from this kind of sloppy analysis. The counts are bounded from below by 0, which violates the assumption of normality of the errors. There's counts near 0, so that both the actual assumption. If you have a bunch of counts and they're nowhere near 0 and they're nice and normally distributed, then even though they're counts, it doesn't matter. You can still use a Gaussian distribution for the residual. But these have counts near 0, so the actual assumption and the kind of intent of the assumption are violated. The variance doesn't appear to be constant. Maybe you could take logs. There are some 0 counts, so you can't take logs. So you can maybe do log count plus 1. But my favorite way to do this would be to do something like a Poisson GLM or a quasi-Poisson GLM or something like that. Then you don't have to worry about any of these issues. Okay, so let's talk. This is an example from Jeff Leek, who's a co-instructor in the class, and he had this nice example when he was covering things like ANCOVA and looking at the Millennium Development Goal 1, which is a study related to a World Health Initiative, World Health Organization initiative studying malnutrition, and they very nicely put their data online, and he shows you how to get the data, but I also have it on the GitHub, the data we pulled on the GitHub repository for this slide, for these slides. So here's where you download the file, but I have it commented out because I have it in the GitHub repository. So here instead you can just read in this hunger.csv this command right here just takes the gender variable and says let's get rid of the specific cases where the gender took this particular value, and then here you can see a little bit about, you can see the data set. This head statement prevents you from having to type, for example, hunger bracket 1 to 10 comma end bracket to print out 10 rows. Head just kind of prints out a couple for you. It has some default number, and it's really a useful thing because it's faster to type out than the brackets. So you can any rate, you can peruse the data a little bit. It has time, it has the has region, country, gender. Let's see, and we're not going to use all of these variables, and there's some missing ones, some ones that didn't get grabbed correctly. Okay, so let's plot the percent of the population that's hungry versus time, starting at 1970, where the start of the data set was. So it's hunger year versus hunger star numeric, which is, I guess, percent hungry. And there's your plot. Okay, and let's see if we can fit this. This is a good example of this kind of sociological data where it's often quite messy and doesn't have these super nice linear relationships like we've looked at in some of the examples. So we have, if we were to fit a linear model, then beta naught would be our percent hungry at year 0, which again doesn't make any. So let's just remind us that doesn't make any sense, right? The data set goes back to 1970, so year 0 is an extrapolation. So the intercept it hasn't been calibrated to an interpretable value. So if you want your intercept calibrated to be an interpretable value, you would need to subtract your year by some meaningful value. You could subtract the average, and then the beta naught would be interpreted as the percent hungry at the average year in the data set. Or for time, that doesn't make much sense either in this data set. You might want to subtract by the earliest year, 1970, and then beta naught will be interpreted as the expected percent hungry, the estimated expected percent hungry at year 0 for the study, being 1970. And then beta 1 is the decrease in the percent hungry per year, and the epsilon, I think you could, so one way to think about the epsilon is everything we didn't measure, which is a nice way to think about it. It's sort of like we've missed a bunch of terms in our linear model, and they all bump up and down, and then in random ways, and we've sort of we're going to treat them all as if they were Gaussian noise. There's other ways to think about this error term, and it depends on things like how you sampled the data, randomization schemes, and things like that. But for right now, let's just say we're thinking kind of mechanistically, and that we missed a lot of things in this model, and we're dumping them all in the error term. Okay. Okay. So the LM1 is the just the standard linear regression model with hunger as the outcome, percent hungry as the outcome, which is this variable hunger numeric, $numeric, and with hunger $year here. I prefer I prefer actually to put the data frame in the data equal statement, by the way. Of course, this works as well. If you don't have the data equal statement, then the variable has to be sort of explicitly stated. You have to grab the variable from the data frame hunger and from both the numeric and the year variables. You have to grab from them if you don't include the data statement, because LM otherwise wouldn't know where to look. Here's the plot, and then you can just do lines. You can, by the way, just do lines LM1, and it'll put it in there. And there's the line. Oh, there's the line. You can see it. And there's a lot of overplotting in this plot, so it's kind of hard to tell the fit. It'd be nice to so maybe when you look at this data, you could do a residual plot and some other things to actually look at the fit, jitter some points, and do some things to see the fit. Maybe we're interested, by the way, in males versus females, so we could color color males and females different colors in the data set, and there's a little bit maybe of a difference between males and females there in terms of the relationship. So let's consider it, and let's think about how we can do it using some of the tools we've learned so far. So H hungry F is the percent hungry among females, and that's and I think I think this is actually a reasonable and important consideration, gender, when considering these kinds of problems, because the different gender roles played at different in different areas of the world. So this would be a very reasonable thing to do. So beta, let's see, beta F0 is the intercept for this model, which is just for girls. Beta F1 is the slope model, the slope for girls. And then we're lumping everything we didn't measure into an error term there. And then we could have the same model for males. And I know it's a little bit Slightly confusing notation, but HU is for the hungry, M for male. B0 is always intercept, B something 1 is always slope, and Y something is always year, and E something is always epsilon. And okay, so what we're saying now is we could try to have these two models, one line for girls and one line for boys. Okay, and you could do that, one way you could do that, right, is fit a separate line, only considering the girls and only considering the boys, and then plot them, and then you get two lines. Okay, and then you see the males in black and the females in red. Okay, and there does appear to be maybe a slightly different slope. There's a lot of points, so that might even be significant. Okay, so that's how you would do. That's looking at this with two separate lines, fit separately. We're going to show you how to do this within a single regression model. With one caveat, I'll tell you there's an important caveat as to what it's doing. This stratifying by gender, everything's different. Intercepts different, slopes different for each gender, plus the residual variance is different, right? You have a different residual variance for each gender. So not only does it have different slope and mean parameters, it also has different residual variance parameters. Okay, so here's one way to do it so that only the intercept changes. Okay, so what I've done now is I put an indicator variable for gender equals male. Okay, so what happens? You get our outcome H is equal to beta 0 plus beta 1 plus beta 2 year. Expected outcome. If the person is male, and it's equal to beta 0 plus beta 1 plus not beta 1, but that guy's gone, plus beta 2 y for females, because this indicator term would be 0. Okay, so what does that look like? That's looking sort of like this, that there should be, we're saying there's two lines, right? And it's encouraging that the lines are going down. What this is saying is that there's a line for males and a line for females, and they share the same slope with respect to year. However, there's a different intercept. Males have this intercept and females have that intercept. And if you were to subtract the two, the difference in the intercepts is beta 1. So beta 1 is the change in the intercepts between the two, whereas beta 0 is the intercept for the females, and beta 1 plus beta 0 would be the intercept for the males. Okay, so that's a way you can fit two lines with the same regression model. You've included an intercept term, you've included an indicator term for gender. You could also just include gender as a factor variable, of course, given our discussion earlier, and you've included year. And the result of that is two lines, one with an intercept for males and one with an intercept for females, but sharing the same slope. There you go. Here's we do it. And we've put in sex here. It treats it as a factor variable. And there, when you look at these two lines, I know it's a little hard to see, but when you do this yourself at home, you'll see that these are exactly parallel. And of course they're parallel because our model said year has no, there's a gender variable that gives us a different intercept for the genders, but that our slope variable, year, is not interacted with gender. Okay? Aha! But let's have lines with different slopes. So now we have an indicator for gender, and we have another indicator for gender, but this time multiplied times year. Okay? And then now let's look at what happens. So here, our expected value of our outcome for males, right, it's beta 0 plus beta 1 if they're male, because that guy will be 1, plus beta 2y, plus beta 3, that guy will be 1, beta 3y, and then the epsilon goes away in the expectation. Okay, and then our expected value of h, this is when they're male, expected value of h when they're female, that's beta naught, plus beta 1, I'm sorry, the beta 1 is not there because that would be 0 for females, so that beta 1 is there, gone. So beta 2y would be there, and then beta 3, this guy would be 0 for females, so that guy would drop out, and so he wouldn't be there either. Okay, and so what is this saying? This is saying there's a line for males, and they have an intercept that is beta naught plus beta 1. There's our intercept. It has a slope, and that slope, notice we could just pull this out, and this is beta 2 plus beta 3 times y, these two terms right here. So it's saying that the slope is beta 2 plus beta 3. I said beta 2 times 3. Beta 2 plus beta 3 is the slope. Okay, and then here it is for females, and their intercept is beta naught by itself, and their slope is beta 2 by itself. So that the interesting part about this is that beta 1 is again interpreted as the change in the intercept, which again, remember the way we've characterized it, the intercept isn't terribly meaningful because it's the percent hungry at year 0, which we don't care about. Beta 1 is the change in the intercept between the two groups. Beta 3 is the change in the slope between the two groups. And notice the variable that we include, the new variable that we included, had an indicator variable times year. Okay, so that all we did was include the indicator variable times year. And so here we fit it. We have our outcome, the percent hungry, we have year, we have gender, and we have gender times year. By the way, if you include, here's a little trick, if you include the asterisks when you do an interaction, it automatically includes the main effects. You don't have to include them. If you, instead of including an asterisk between the two, if you include a colon, 2 dots, right? If you include a colon, then it only does that. So for whatever the reason, if you want something that includes the interaction term but not the associated main effects, then you put in a colon. If you want it to include the interaction term and all the lower order main effects, then put asterisks. And there you can see now we fit 2 lines. It's maybe a little hard to see, but I think I can see it. Yeah, anyone can see it, right? Look at the difference in lines there and the difference in lines there. They have both a different intercept and a different slope. One for males and one for females. Okay. And so here is our regression output. So let's see. So females are the reference category. It's clear, right? Because we are getting coefficients for male and it's omitting the coefficients for female, so it must be setting female as the regression coefficient. So this is giving us the intercept and the slope for females. This guy is the change in the intercept for males, so that the sum of these two is the 603 and 61 is the intercept for males. And then the sum of -2 and -0.03 is the change in the intercept between genders, and so the change in the slope between genders, and so our new slope for males would be the sum of those two. Okay. Notice, of course, the two terms that ascertain whether there's a different intercept or a different slope between genders are these two, and they don't appear to be very important, which of course makes sense, because if you look at if you look at these things, they don't look altogether that different, right? There's a lot of data, so you might conjecture that the intercepts might look different, but the slopes, it clearly doesn't look like much of anything. Okay. So I just want one slide on interpreting a continuous interaction because it's kind of hard. Not hard. Hard isn't the right word. It's like hard in the sense that programming your DVD player is hard. Though I guess no one has a DVD player anymore. If you used to own a DVD player, it's sort of that kind of hard. Not hard, but you have to look at a manual. Okay, so imagine if I have an outcome y and I have two predictors x1 and x2. Okay? And here's my model. I have an intercept, I have a main effect for x1, I have a main effect for x2, and I have an interaction. And I'm not going to assume that x1 and x2 are binary. Neither x1 nor x2 are binary. So I can't do the kind of separate line type interpretations that I was doing on the previous slides. You have to think about it differently. But it's not that hard, so let's just go through it. If I were to look at y and look at if my x1 was some value plus 1 holding x2 constant, minus the idea that it was just x1 not with the plus 1 holding x2 constant, I now get beta 1 plus beta 3 x2. And if I didn't have that interaction term there, it would just be beta 1 by itself. So it's no longer the case that beta 1 is interpreted as the expected change in y per unit change in x. Instead, beta 1 is only interpreted that when x2 is in fact 0. Okay? And instead, if you want the expected change in y per unit change in x1 holding x2 constant, you actually need to know that whole thing. Okay, and it's of course convenient to think about this when x2 is binary, because then you can just say it's beta 1 when x2 is 0, and it's beta 1 plus beta 3 when x2 is 1. But if it's continuous, then you need it varies. The change in the slope varies as x2 changes. Okay. So, but notice we can get an interpretation for beta 3. Okay, so we can take the change in the expected value of y given a 1 unit increase in x1, where x2 is held at x2 plus 1, right, versus the change in y, expected change in y for a 1 unit change in x1, given that x2 is held at x2. Subtract those two, right? That's this top one is beta 1 plus beta 3 times x2 plus 1, and this bottom one is beta 1 plus beta 3 x2, and so if you subtract those two, you just get beta 3. So beta 3 then is interpreted as a change in a change. Beta 3 is the change in the expected change per unit x1 per unit change in x2. Okay, right? It's a change in a change. That's how you wind up interpreting intercepts, right? Our intercept if our slope was the expected change when we had an interaction with the slope in a binary variable, then the interpretation of that interaction was the expected change in the slope comparing the two groups. Well, if the interaction variable isn't a grouping variable like gender, it's interpreted like this here. Okay. So this is a change and this is a change. So beta 3, the interaction term, is interpreted as a change in a change. Okay. So here is our outcome again, which is the percent hungry. Here is our intercept. Here, IN in this case is income. We're putting income in as a variable. Okay, so here we have income, year, right? Beta 1 for income, beta 2 for year, and then beta 3 for income times year. Okay, so beta 1 is the change in percent hungry for each dollar of income in year 0. Beta 2 is the change in percent hungry in 1 year for children whose parents have no income. Again, just hearkening back to my notation here, right, in that these guys are interpreted this way with respect to, only when x2 is 0 do those guys make sense. Now, by the way, no income is probably a reasonable variable value for income, or not. There's probably low incomes that relative to the larger incomes could be close enough to 0 to call it no. Time equals 0. Year 0 doesn't make any sense. So if you want to, again, it's another one of these things, just like the intercept. If you want to interpret these things, you might want to subtract the income in year from a value that you actually want to interpret it relative to. Maybe the baseline year, 1970 for year, and maybe average income for income or something like that. Then that would yield a beta 1 and a beta 2 that are interpretable at the level that you want. Okay. So then beta 3, right, our interaction term is the increased change in percent hungry by year for each dollar of income. Okay. And then this just reiterates the equation we had from the previous page, but just in this context. And epsilon, in this case, is, again, we're lumping in everything we didn't measure. And Jeff had a comment here, and this is, of course, very well put forward, is that interactions are kind of complicated, so you need to be careful. I almost find it's almost always useful to write out the interaction. Just to be mean, I always used to, in oral exams for PhD students, I would kind of write out some complicated interactions and ask them to tell it what it means on the board. And these are people that study statistics, and they would almost always have to write it down. What I would mention is just whenever you have an interaction, an interaction, actually kind of write out the model and see what it is. We kind of give you I give you the relevant formulas on this page right here, and if you go through that exercise, you can't mess it up. But if you don't go through that exercise and you just look at the output right away, and you think and you kind of thoughtlessly interpret the coefficients, then you can screw it up pretty easily. So I think that's the general theme of this lecture. For example, with factor variables, I've seen people screw up interpretations of factor variables by forgetting which is the reference level, or forgetting whether or not they included an intercept. And those things all very dramatically change the interpretation of those coefficients. Okay, so that's the end of the lecture, and we'll look forward to seeing you at the next lecture. Not seeing you, I guess you hearing me at the next lecture.